Okay, so today, first we are starting with analysis of variance. In analysis of variance, in the left-hand side of the regression equation, we consider the total variation in y around y bar. Total variation in y around y bar. In other words, we are considering the term summation yi minus y bar whole square. How yi is varying around its mean value that we measure. And we decompose this into two parts. Explained variation, that is with the help of explanatory variables, how much of this variation can be explained, and there will be always some unexplained part, and this unexplained part will give us the residual component. Okay, so what is happening? There is some average demand for orange, and looking at the data, we are trying to find out how the demand is varying, regular demand is varying with respect to this average. Okay, so variation of demand for orange for every individual around some average demand, that is giving the total variation or total sum of squares, total variation, which we call TSS, total sum of squares. And that we are dividing into two parts. Suppose we are considering the price of orange. So how much of this variation can be explained by the price of orange, and how much the price could not explain? The price could not explain, we are keeping in the residual part, and the price could explain, we are keeping in the explained part. So notationally, TSS is summation small yi square, which means capital Yi minus y bar whole square. ESS generally we present by beta hat square summation xi square. That means beta hat square summation capital Xi minus x bar whole square. However, ESS can be presented in two ways. We can present it by beta hat square summation Xi minus x bar whole square, or we can present it as beta hat into summation Xi minus x bar into Yi minus y bar. Let's check this thing once again. I am telling that this is equivalent to in a simple regression model. In a simple regression model, beta hat OLS is given by summation xi yi divided by summation xi squared, or summation capital Xi minus x bar into yi minus y bar divided by summation xi minus x bar whole square. Okay, so summation okay, so in this expression, if I take one beta hat out of this beta hat square, and I consider this to be beta hat into beta hat summation xi minus x bar whole square, this can be replaced, the second part can be replaced by summation xi minus x bar into yi minus y bar. So beta hat square summation xi minus x bar whole square can be presented by beta hat into summation xi minus x bar into yi minus y bar. So there is an equivalence between beta hat square summation xi minus x bar whole square and beta hat into summation xi minus x bar into yi minus y bar. So ESS can be presented using either of the two formula. So it can be presented by beta hat square summation xi square, or it can be presented by beta hat summation small xi yi. Residual sum of squares, we know that will be presented by summation ei square. Now, we will like to establish the relationship that TSS is equal to ESS plus RSS. Total sum of squares is equal to explained sum of squares plus residual sum of squares. To do this, we are starting with summation EI square, the residual part. Now, by definition, the residual is the gap between the observed and the estimated. So it is summation yi minus yi hat whole square. I am taking the difference between yi and y bar and adding one y hat bar. I'll show that y bar is exactly equal to y hat bar. So first I am rewriting the expression as summation yi minus y bar minus yi hat plus y hat bar. So if you look at this, y bar, that is equal to alpha hat plus beta hat x bar. Now if you consider y hat, what you are getting? Alpha hat plus beta hat xi. So if you consider summation of this entire thing and divide it by n, you will get back the same term. Y bar will be equal to y hat bar is equal to alpha hat plus beta hat x bar. Now to explain the thing in a better way, let me consider a standard simple regression model. Now, okay. Now, if I divide both sides by n alpha by n, okay, and under the classical framework, this is equivalent to 0. So, we are getting okay. The next term was y hat. Following the same logic, you know, what we can, sorry, yi hat. You can consider if you divide both sides by n, okay. So now if I replace all these unknown coefficients by the estimated values, you know, the structurally both the things are same. So y bar is equivalent to y hat bar. Okay. So y bar is equivalent to y hat bar. Structurally, both the things are same. Under a particular context, we will get the fixed values of alpha and beta. For a particular sample, you will get the fixed values of alpha and beta. So we can replace y bar by y hat bar and can write the format in this way. This we can present as small yi, capital Yi minus capital Y bar. This is given by small yi and minus yi hat minus y hat bar, that is given by beta hat xi. Yi hat minus y hat bar, that is given by beta hat xi. Okay, so please check whether I'll get beta hat xi if I take the difference between yi hat and y hat bar. Are we getting the difference to be beta hat xi?
Yes, ma'am.
Okay. So, if you understand this thing, we are presenting summation ei square as summation yi minus beta hat xi whole square. So coming to the next step, or summation ei square, I am considering this whole square, summation yi square plus beta hat summation xi square minus 2ab minus 2 beta hat summation xi yi. Now beta hat or summation xi yi, already from our rough work, we know that will be beta hat summation xi square, or alternatively you could work with this term too. So you can work with this term or you can work with this term. Okay, so whatever you like. So if I replace summation xi yi by beta hat summation xi square, we are getting summation ei square is equal to summation yi square beta hat square summation xi square minus 2, if I replace this by beta hat summation xi square minus 2 beta hat square summation xi square. So 1 beta hat summation xi square will be cancelled. Now the equation can be rewritten as summation yi square is equal to beta hat square summation xi square plus summation ei square. So I am bringing summation ei square here, summation yi square I am bringing to the left and adjusting the signs. So ultimately I am getting this result. This summation yi square is presented as TSS, beta hat square summation xi square is presented by ESS, summation ei square that is presented by RSS. You could write the ESS as beta hat into summation xi yi 2. So ESS can be presented either by beta hat square summation xi square, or it can be presented by beta hat summation xi yi. Okay, so for this expression, there is a chance that you are, while here you are using this kind of expression, summation xi yi, you are replacing by beta hat summation xi square. You could do the thing in a different way. You can write 1 beta hat summation xi square, that as summation xi yi. From here you can take 1 beta hat, okay, and you can keep 1 beta hat and another beta hat you could separate out, and this you could replace by summation xi yi. Okay, so in that case you will have beta hat into summation xi yi here, and that you can adjust with this minus 2 beta hat summation xi yi. So you will get minus beta hat summation xi yi. So in place of this term, basically you will get after adjustment of signs, etc., beta hat summation xi yi. Okay. So this is another possibility. This is another possibility. Whatever be the thing, the main essence of this entire discussion is using the analysis of variance method, we can present TSS, or total variation in yi, as the sum total of ESS and RSS. Or, you can say that the residual component or the residual sum of squares should be TSS minus ESS. Okay. So now if I go back to our numerical exercise, I'll be able to use this kind of formula. Okay. I'll be able to use this kind of formula in place of RSS, Okay. We are understanding RSS is basically summation yi square minus beta hat square summation xi square. So all these values I have with me, summation yi squared, beta hat squared, summation xi squared, this kind of values we will be able to derive using the values given and the values of the beta hat derived by me, and I'll be able to find out what will be the variance covariance matrix of beta hat. Now, before switching to the numerical exercise, let's look at the note. It shows that the total variation in the observed y value about their mean value can be partitioned into two parts. One attribute to the regression, that is the explanatory part, and the other to random forces, because not all actual y observations lie on the final line. Okay, you will find the observations are around the feet. All the points of the scatter diagram will be not there in the feet, so there are some errors. So variation in yi partly we will be able to explain by the feet, because some of those observations will be on the line. However, some of the observations will not lie on the line, so there will be some residual components as well. Okay, so this is the meaning of these analysis of variance. TSS is equal to ESS plus RSS. Any question regarding the derivation, regarding the meaning of all these things? Is it okay to all of you? Is it fine? Okay, so if it is fine, let's go back to the numerical exercise and let's try to complete that exercise. We tried to, calculate the, we are here. We need to calculate, sorry. We need to calculate the RSS. Okay. Sorry. We need to calculate the RSS. The RSS value in terms of matrix algebra. Okay, so this can be written in this way, or this is equivalent to beta hat square. Sorry. There will be one square. Okay, so both the possibilities are there. So you can use either of the two formula. So since in the second formula we need to calculate the square, etc., so it will be better if I use the first formula. So use this one. Use the first formula. is this. হ্যালো, হ্যাঁ বলি, হ্যাঁ হ্যাঁ না আমি ভুলে গেছি পাঠাতে, আসলে কন্ট্রোলার্স ডিপার্টমেন্ট হঠাৎ করে বলেছে তো। হ্যালো, সরি। So y prime y, what is the value of y prime y? It is, I think, 60. So let me check. Yes, summation y square was 60. Okay. So the value of y prime y will be 60. Beta hat prime. Okay, so there will be beta hat prime, sorry. The formula will be beta hat prime x prime y. So I have to take the row vector of beta hat values. Your beta hat values was 1.40, the first one.
Yes, ma'am.
Second one.
1.40, 0.2, and minus 1.8.
These are the three values, right? And that will be multiplied with x prime y. And x prime y values are 7, minus 7, minus 26. So this will be the RSS value. I didn't mention about the number of observations. Number of observation is 24. N is equal to 24. And N minus K. So what is the value of K here?
4.
4. Very good. Because now we will not consider the deviation form. We will consider the total number of unknown parameters there. So I have 3 betas along with x1, x2, and x3, and I have an intercept term. So I'll consider total number of parameters to be 4. So n minus k is equal to 20. Now what is the value for this RSS? What is the value here? I hope everybody is understanding this will be a scalar. Last day also I discussed this will be a scalar. And if you look at in terms of the matrix algebra, here beta hat prime, that is 1 cross 3, and this value 3 cross 1, so it will be 1 cross 1, so you will have a single value here. So if anyone can complete this thing, please tell me the value of RSS.
Ma'am, 4.8.
4.8, yes. So check whether you are getting the value 4.8. Once you get this thing, we will go back to calculation of variance of beta hat. In place of sigma square, we are putting the value RSS by n minus k, and then I have to write x prime x inverse. So already you have x prime x inverse. So I think this is, and the inverse value is there. Now, once you multiply this 0.24 with the x prime x inverse, you are getting the entire variance covariance matrix of beta hat. Diagonal elements are variances, whereas the off-diagonal elements are the covariances. So if anyone can complete, the derivation of variance of beta hat, please tell me the results. I'm waiting for the result. What will be the first value? Anybody got it? Is it this?
Yes, ma'am.
Second one?
Minus 0.012.
Very good. It is a symmetric one. So more or less this will be the value. So remember the diagonal terms, this is giving you the variances, whereas the off diagonal terms, these are the covariances between different beta values. So all these diagonal terms, these are the variances. Variance of beta 2 hat, 3 hat, 4 hat, etc. And off diagonals are the covariances. So in this way, numerically, we can do these things. So are you getting these results more or less? Some of the values you mentioned and others I think are coming in this line. Any question, any doubt, anyone? Anyone has any question? Or you could follow everything properly? Ritoja?
Yes, ma'am.
Could follow everything properly?
Yes, ma'am.
Okay. Twinkle?
Yes, ma'am.
Okay. So let me start talking about the next thing. Now I'll discuss about different types of correlation in context of a multiple regression. When we introduce more than one explanatory variables in the model, we will have three types of correlations in our analysis, and these three correlations are totally different from each other. The three types of correlations we are going to discuss are multiple correlation, partial correlation, and simple correlation. It is not that in two variable case we cannot identify these issues. Okay, the problem with the two variable case is there we have a single explanatory variable and therefore multiple correlation coincides with partial correlation.
Ma'am,
Yes.
I'm sorry to interrupt you, but I have an emergency in my home. Can I please leave the class?
Yes, all these things, earlier also I mentioned you should send the mail earlier. Okay, not
No,
during,
ma'am.
you should mention all these things. Yes, please leave.
Okay, ma'am. Thank you, ma'am.
So, three types of, in two variable cases also, as I mentioned, we can identify these things. However, there will be, no difference between the two, between these three types of correlation. Simple correlation will be equivalent to the partial correlation. Partial correlation will be equivalent to multiple correlation, etc. So, before understanding the nitty-gritties of these correlations, let me very quickly try to give you the definition of these three correlations. The first, I'm talking about multiple correlation. Okay, multiple correlation is generally presented using capital R square. Now, in case of multiple correlation, look at the, presentation, you will find that y I am considering here, then dot, and then considering the entire set of explanatory variables. So how the entire set of explanatory variables can explain yi? Yi given x1, x2 to xk, which means given all the explanatory variables together, how this can explain the variation in yi. Next, we consider simple correlation. Now, in case of simple correlation, you can consider yi and any of the xi or few of xi's, or we may consider the correlation between only among xi's, only among xi's. This concept, that is the correlation only among xi, this will be very, very important in our entire discussion, because this will give us some idea of multicollinearity, if there is any. That is, whether there is linear relation among all explanatory variables. Okay, this is the notion of multicollinearity. We have to discuss about this thing in our regression diagnostics section. One of the crucial assumptions in context of a k-variable analysis is we need a full column rank. We need a full column rank, or we need linear independence between all xi columns. However, if we find that these simple correlation among all xi's, these are very high, this is very high, in that case, there is a typical type of problem, and that problem is identified as multicollinearity problem. If there is this kind of problem, we need to remove the multicollinearity issue to get the reliable estimates of the parameter. Okay, so concept of simple correlation, that is very, very important. Simple correlation you can consider between yi and any set or subset of xi's. However, if you consider the correlation among the explanatory variables only, not bringing the explained variable in your analysis, that will be very, very crucial for our future discussion or discussion regarding the regression diagnostics, because it may give us some clue whether the assumption of full column rank holds or not. The third variety is the partial correlation. In case of the partial correlation, we present the correlation with the help of small r. However, what here we are getting, I'm considering yi and any of xi. In first example, I'm considering x1i. In the second example, I'm considering x3i. Then I am bringing this dot, that means given, and I'm writing rest of the explanatory variables. Here x2i, x3i up to xki. Here x1i, x2i, then x4i up to xki I am considering. Okay. So here I am taking one particular explanatory variable and taking a correlation between that variable and yi given or conditioned on the presence of other explanatory variables. In case of a simple correlation, I am considering y and the entire set of xi or subset of xi. However, I am not applying any kind of condition there. Whereas in case of the partial correlation, I am putting the condition, I am looking at the relation between yi and any one of the xi's given the others. This partial correlation is also very, very important in context of multiple relation. Each of the regression coefficient is basically related with the notion of partial correlation, regression coefficients. Okay. So let's write the regression model once again. Regression model. that is given by this is the structure of the regression model. Now, if I look at these beta 2 measures the relation between yi and x2i given rest of the explanatory variables. So beta 2 is basically talking about what proportion of the variation in yi can be explained by x2i given rest of the explanatory variables, given x3i, x4i up to xki. Similarly, if I consider beta k, this beta k, this indicates how xki can explain the variation in yi given x2i up to xk minus 1i. So all of the regression coefficients are basically trying to estimate the variation which can be explained by the associated explanatory variables given the rest. So the notion of the regression coefficient is associated with partial correlations. It is, the explanatory power of x2i is conditioned on what other variables are explaining. Similarly, explanatory power of x3i is again conditioned on total variation explained by rest of the explanatory variables. So in this way, in our future discussion, you will find that we are relating the regression coefficients with the notion of partial correlation. So what we are finding that each of the correlation has separate roles. In our next discussion, we will start with the multiple correlation, capital R square, where we are considering explanatory power of the entire set of explanatory variables to explain the variation in yi. So on one hand, I have TSS here, total variation in yi, and in the other hand, I have ESS here because I am considering the entire set of explanatory variables. So we will find that these multiple R square, which is the first one, this multiple R square can be presented as ESS by TSS. And this will appear as the measure of goodness of fit. Okay, because how all the explanatory variables together can explain the variation in y. Now, if it can explain almost the entire variation in y, in that case, we are understanding that most of the scatters are lying on the fit. So if this is the regression plot in a two variable context, if we find that most of the observations, are lying on the feet, in that case, ESS is moving towards TSS and R square will move towards 1. However, under most of the circumstances, this will happen. Only a few observations are there and it will be like this, this kind of thing. Okay, so there will be a gap between ESS and TSS. If most of the observations lie on the feet, it will move towards 1, and if none of the observations lie on the feet, in the worst case, the value will be 0. Okay, so variation in yi is not explained by the feet in that case. However, as we are considering the total variation in yi on one hand and the power or explanatory power of all the explanatory variables on the other hand, we can define goodness of fit using the term ESS by TSS, and we will show an equivalence between R square and this ESS by TSS. So let's first focus on multiple correlation R square and check how this can be presented by ESS by TSS. Now again, we are starting with the two variable classical linear regression model because already you did all these things. When y is regressed on x, beta hat value that becomes covariance between yi xi divided by variance of xi, because beta hat is summation xi minus x bar into yi minus y bar, and in the denominator we have summation xi minus x bar whole square. So beta hat can be easily presented as covariance between xi yi divided by variance of xi. If you consider the reverse regression, that is x is regressed on y, the concept will be similar. However, in the denominator we will have variance in yi rather than variance in xi. So beta hat xy will be covariance xi yi divided by variance of yi then. Okay. Now, if we consider the R square, the Pearson's product moment formula for R square, the formula will be covariance square divided by variance of xi into variance of yi. So, it can be presented by beta hat yx into beta hat xy. Okay, so this is the additional thing I am considering here because there may be some numerical exercises, or this is also an important relationship. Many a times we need this kind of relationship. Okay, the correlation is actually product of regression coefficients, where the first one is result of regressing y on x, and second one is the product out of x is regressed on y. Okay, now let's go back to the definitions, etc. Okay, so when we are considering this kind of relation, etc., R square is equal to beta hat summation xi square whole square. So covariance formula I'm writing as beta hat summation xi square. Now how I am doing that? Look at this beta hat yx. It is covariance yi xi divided by variance of xi. So it is summation xi minus x bar into yi minus y bar divided by summation xi minus x bar whole square. So beta hat into summation xi minus x bar whole square, that is equivalent to this covariance term beta hat into summation xi minus x bar whole square is equal to this covariance. So in R square formula, covariance I am replacing by beta hat into summation xi minus x bar whole square, or beta hat into summation small xi square, and I have a square of the thing. So I am considering the square. In the denominator, variance of xi into variance of yi, so summation xi minus x bar whole square into summation yi minus y bar whole square I am considering. So, here I am getting beta hat square, square of summation xi square. So one of the summation xi square will be cancelled with the denominator. So we are left with beta hat square summation xi square, and in the denominator summation yi square simply. Now this numerator is nothing but ESS. Already we worked with this beta hat into summation xi yi, or beta hat square summation xi square. These are the indications of ESS, explained sum of squares. So this is ESS. And the denominator is nothing but TSS. Okay. So this, we can, starting with these R square xy, we can reach at a term which is ESS by TSS. In a multiple regression model, this, instead of presenting this in terms of small r square, we present this ESS by TSS by capital R square. Okay. In a k-variable analysis, multiple correlation or coefficient of determination is the relation between explained variable y and the number of explanatory variables x1, x2 to xk. It is presented as I mentioned, r squared dot x1, x2 to xk, or you can simply write 1, 2 up to k, where this 1, 2 up to k are indicating the explanatory variables present in the model. And now we got, this is nothing but ESS by TSS. The ESS is given by regression estimates. Okay, so next, we can present this ESS by TSS as, the numerator as TSS minus RSS. This ESS is basically TSS minus RSS, okay? So TSS by TSS is equal to 1 minus RSS by TSS. So this is an alternative presentation of R square. R square can alternatively be presented as 1 minus RSS by TSS. Now, if the definition of R square is equal to ESS by TSS, as we increase one explanatory variable in our model, this ESS by TSS will always increase, The explanatory variable may be very small power to explain the variation in yi. However, by the structure of R square, as we incorporate a new explanatory variable, always there will be some increase in ESS, and therefore ESS by TSS will always increase. So in a multiple regression analysis where there is a scope that you will consider a number of explanatory variables, remember, as we incorporate one more explanatory variable in our analysis, always R square will increase because ESS by TSS will increase, TSS remaining constant. As we incorporate one new explanatory variable, ESS increases, and thereby ESS by TSS will always increase. Okay. So let me close some of the. So what I am telling that, constant, and is it okay to all of you? As you incorporate one more explanatory variable, ESS by TSS will continuously increase. Is it okay to all of you? Are you understanding?
Yes, ma'am.
Now, the question is whether indefinitely you will go on and on in increasing the number of explanatory variables or not. Because you are finding that suppose you are starting with the demand equation when there is price of substitutes, price of complementary goods and income. Then you are bringing taste and preference. Then you are bringing geography. Then you are bringing demography. Then you are bringing gender. Then you are bringing education. Then you are bringing parental education. Go on and on and on and on. You will find that your explanatory power is somehow improving and ESS by TSS is increasing and your goodness of fit therefore is increasing. So the question is therefore whether in a multiple regression analysis you will go on and on doing this thing, you will indefinitely incorporate the new explanatory variable in the model or not. The answer is no, because when we are increasing the number of explanatory variable in the model, it is true that the explanatory capacity of the model is increasing. However, on the other hand, there is a loss too. This is the gain part. So this is the gain part. This is the gain of incorporating a new explanatory variable. However, there is a loss too. Now, what is that loss? As K increases, N minus K, what is N minus K? Degrees of freedom. That is falling. N remaining constant. As you are bringing a new explanatory variable, that is bringing a new parameter in your model. First, suppose we are starting with two explanatory variable. So my model is yi is equal to beta 1 plus beta 2 x2i plus beta 3 x3i plus ui. Then you are bringing another explanatory variable x4i, so beta 4 is coming. Then you are bringing another explanatory variable x5i, 5i, so beta 5 is coming, and the things are going like that. One more explanatory variable means you are bringing another unknown parameter in the model. So as you are increasing the number of parameters in the model, number of observation remaining constant or n remaining constant, n minus k is falling. You are losing degrees of freedom in your analysis. So this is the loss part. Hence, you have to make a balance between the gain and the loss part. You have to make a trade-off, or you need to make an optimization so that you get sufficient number of explanatory variables. However, you do not face substantive loss in degrees of freedom. The concept of degrees of freedom, that is very, very important for running a good regression, because this is the feasibility condition. Okay, so we cannot go on and on increasing the number of explanatory variables in our regression model. We have to stop at a point where we should have a sufficient degrees of freedom. So what we are finding that R square, which is ESS by TSS, as a measure of degrees of freedom, cannot capture the loss part. It can capture the gain part. However, while we are increasing the number of explanatory variables in the model, there is some loss in degrees of freedom, and this part also we need to incorporate in our analysis. Okay, however, R square has a limitation to do that. So we move towards a better measure of goodness of fit and improved measure of goodness of fit, which we call the adjusted R square. Which we present by R bar square. So what we are finding that R square as a measure of goodness of fit can incorporate the gain part. However, somehow it cannot incorporate the issue of loss here. In a regression model, always we need to make a trade-off between the gain part and the loss part. So we will move to a better measure of goodness of fit, which we call adjusted R square and present by R bar square. In case of R bar square, it will be very, very similar to that of R square. However, each of ESS and TSS will be deflated by its degrees of freedom. Sorry, just a minute. So I presented R square as R bar square will be okay, or you can write it in terms of ESS and TSS. Then also you have to deflate ESS and TSS by respective degrees of freedom. While R square, cannot capture the loss part, R bar square can capture both the gain as well as the loss part. Therefore, in our rest of the analysis, as a measure of goodness of fit, we will concentrate on adjusted R square, adjusted multiple R square or R bar square rather than R square. Okay, so as we incorporate a new explanatory variable in the regression model, there will be a twofold effects. ESS improves, TSS remaining constant, and therefore ESS by TSS increases. However, there will be a loss in degrees of freedom as K increases, N remaining constant. R square as a measure of goodness of fit fails to capture the second effect, and therefore we need an improved version of goodness of fit capturing both the above mentioned effects. R square after adjustment for loss in degrees of freedom can be presented as R bar square, 1 minus RSS by N minus K by TSS by N minus 1. We can adjust the things in this way. It is 1 minus N minus 1 by N minus K into 1 minus R square, because R square is 1 minus RSS by TSS. So it can be presented in this way. And হ্যালো শাশ্বতী, আমি ক্লাস নিচ্ছি তো এখন, আমি নিচ্ছি তো। Okay, so 1 minus R bar square is equal to N minus 1 by N minus K into 1 minus R square. So from there we are getting 1 minus R bar square is equal to N minus 1 and there is 1 minus r squared divided by n minus k that I am representing as SU squared by TSS. Okay, so this part is there. N minus 1 you are understanding. However, this 1 minus r squared by n minus k that I am presenting by SU squared by TSS. Okay, so would you please try this part and check whether you are getting this or not from your 1 minus r squared by n minus k part. SU square, remember, that is RSS by TSS. RSS by n minus k. SU square is equal to RSS by n minus k. SU square is equal to RSS by n minus k. Okay, and what you need to check this one, 1 minus r square by n minus k. That we are presenting by SU square by TSS. Are you getting this? So look at this relation. Okay. So you are getting the clue? Are you getting it? RSS is anybody got it? If you get it, please let me know.
Yes, ma'am.
You are getting it?
Yes, ma'am.
Yeah, please tell us the steps. Please tell
Ma'am,
us the steps.
ma'am, R square equal to 1 minus RSS by TSS.
Okay, so you are starting with this one. So let me, you know, Yes. Now tell me what you are doing. I'm writing simply. R square is equal to?
1 minus RSS by TSS.
Yes.
1 minus RSS equal to
1 minus RSS or 1 minus R square?
sorry ma'am, 1 minus R square
Yes.
RSS by TSS.
Yes.
Ma'am, 1 minute ma'am.
Then
Then ma'am, RSS equal to SU
SU square into N
square
minus
into N minus K by TSS.
by TSS.
Yes ma'am.
Or 1 minus R square
1 minus R square by N minus K equal to. Yes ma'am.
Very good. So these are the steps. Very good. Very good, Rudra. So
Ma'am, I
these
am Orkodeep.
oh, Orkodeep. Okay, sorry. When I'm looking at the things, I'm not getting your face. Okay. Very good, Orkodeep. So we are getting the things in this way. So 1 minus R square by N minus K is basically SU square by TSS. So I'm coming back to the derivation. I started with R bar square, presented R bar square in terms of R square. Also, I'm trying to present R bar square in terms of SU square, because later we need these relation. So thus, we are finding that there exists an inverse relation between R bar square and SU square. So first, we are introducing the measure of goodness of fit. We are finding that we can start with multiple correlation, which is ESS by TSS. However, we are recognizing there is a gain part and there is a loss part. ESS by TSS can capture the gain part, but not the loss part. So we need an improved measure which will be able to capture both the gain part as well as the loss part. So we are moving to the notion of adjusted R square. We defined adjusted R square. We checked the relationship between adjusted R square and R square. We also presented a relationship between adjusted R square and SU square. Okay. And we are coming to the conclusion that adjusted R square and SU square are inversely related. Adjusted R square and SU square are inversely related. In context of our hypothesis testing, we will bring this aspect that there is an inverse relationship between SU square and the adjusted R square, which we are considering as the measure of goodness of fit. So later this relation will have an important role in context of hypothesis testing. So therefore, while we are discussing the idea of R bar square, we introduced the relationship between R bar square and SU square. And I hope you got the steps which Orkodeep told us, and you are understanding, yes, this part can be presented in terms of SU square by TSS. 1 minus R square by N minus K can be replaced by SU square by TSS. Okay. So for today, this is all. Next day, I'll talk about the simple correlation. I'll talk about the partial correlation, and then I'll move to the idea of hypothesis testing. Now, since I have started to discuss the numerical exercises, now it will be your task to derive several, to practice several numerical examples. Okay. So you consider or go through first the Johnstone's book. Okay. And you will find the similar kind